All right, so I want to show you another population model called a competition model. Okay, so for the competition model, we're going to have two populations that feed off of a common resource. Okay, not each other. Okay, so it's not that, it's not like the fox and the rabbits, right? Because the fox eat the rabbits. Um, let's say X is a rabbit population, Y is a squirrel population. Okay. Um, okay. So here are the assumptions for the competition model. Um, Number one, we are assuming here that we have limited resources, which means that we're dealing with logistic growth, which we did learn a little bit about that back in chapter 2. Okay. Um, but then we're going to have a competition term, x times y, which is a lot like the interaction term for x, for the predator-prey model, x times y. Um, Basically, if x, the bigger x times y gets, that means the more competition there is, and really that's bad for both populations. Right? The more competition there is, um, the more the more rabbits and squirrels are gonna have limited resources, so that's not going to be good for their populations. So here's the equations you would get. X prime, okay, so the rabbit population, we're assuming that it would grow logistically, so that would be something like ax minus bx squared. But then we're also going to mix in a negative competition term, so minus cxy. Okay, the ax squared minus, or I'm sorry, the ax minus bx squared, that's logistic growth from chapter 2. So all we're doing to that is we're tacking on that negative competition term. Okay. And then the same thing for y prime. Y prime would be something like dy minus ey squared, right? It would grow, right? The squirrels would grow logistically. Um, but then we're also going to tack on a negative competition term on there. Okay. So this is what the competition model looks like, right? A, B, C, D, E, F are just, coefficients. Okay. Um, it turns out we've already done a competition model problem. Example 2 from 6.2 is competition. Okay. Um, if you look back to the notes from the previous section here, um, example 2 was exactly right. It just, it put in some numbers into that competition model. Okay. So, we've already found all the critical points, right? We found, we found 4 critical points. Um, we even, we even looked at, what the graphs of the different trajectories look like. So what I want to do is basically revisit that graph, um, now with the understanding that x and y are representing populations that are changing over time, and we'll get an idea of what does that mean for like the long term, right? What's going to happen to the rabbits and the squirrels over time. Okay. So what I've done is I've typed the equations into my phase plane drawer, and I got a good window so that I could see all the critical points, and I clicked on a lot of different solution curves. Okay, so what I'm going to do, yeah, that's a good window there. So let me take a picture of that. Okay, here's what here's what the graphs look like. But here, the X is the rabbit population, and on the Y-axis is the squirrel population. Okay, and what we're going to see here is that depending on the initial conditions, one of two things is going to happen. Okay, let's look at, let's suppose our initial condition is this purple point right here. Okay, let's suppose that at some point in time, the rabbit and squirrel population is equal to whatever the coordinates of this purple point are. Okay, well then as time increases, the populations are gonna follow this. They're gonna follow the arrows, right? They're gonna follow the solution curve. Which, notice what's going to happen is going to approach this equilibrium point here of 0.32. Okay. Well, the equilibrium point 0.32 means that if you're on that purple trajectory, as time increases, the rabbit population is approaching 0. The squirrel population is approaching 32. Okay, that's a bad deal for the rabbits, right? In other words, the rabbits are dying out, the squirrel population stabilizing. In other words, the squirrels have won this competition. Okay, and you notice there's a lot of different solution curves that would approach that, that would approach that same kind of conclusion of the squirrels, the rabbits dying out and the squirrels, stabilizing. Right, for example, if your initial conditions were down here at this other purple point, right, that solution also approaches the same long-term behavior. But notice that there's other solution curves which behave differently. For example, if your initial conditions were this green point right here, what's happening? You follow the arrows. As time increases, we're approaching a different critical point, right? We're approaching this critical point, which is 28, 0. So if you're on one of those green trajectories, it's a really different conclusion. As time increases, the rabbit population is approaching 28. The squirrel population is approaching 0. Okay, very, very different conclusion. And notice that's not the only solution curve, right? There's solution curves down here which approach that same, right? That same, right? So those, both of those green ones approach the same conclusion. Okay. Notice there, none of the solutions approach 0, 0. So they're, it's never going to be the case that they both die out. It's going to be either one or the other dies out. Okay. Now, graphically, there's something really important that happens. If you click on enough of these solution curves, you'll notice that basically there's a couple of lines in here. There's a couple of lines in here that approach Both of these lines approach that saddle point kind of in the middle. That blue line there is really important. It's called a separatrix. And what that does is it kind of separates the plane into two halves. Um, if you are above the separatrix, then your solutions are going to approach the equilibrium where the squirrels win. If you are below the separatrix, you are going to approach the other equilibrium point where the rabbits win. Okay, so knowing what so see, notice that you could have two solutions that you could have 2 points that are really close here, but if they're on different sides of the separatrix, as time increases, those two solution curves are going to do very different things. Either the rabbits are going to die out or the squirrels are going to die out. Okay. Um, so yeah, so in practice, it would be really important to know what that separatrix was, because that way you could predict, depending on what the initial conditions are, you could predict um, which population is gonna stabilize and which one's gonna die out. Okay, so that's kind of what's going on with this competition model. Um, there's a lot of other population models out there. Some of them are described in the book. They all have to do with different assumptions about the two populations. Um, but a lot of times the populations, they're either going to they're going to always be drawn towards either one equilibrium or another. Um, so it's important to be able to classify those, right, as either nodes or spiral points, or the idea of being stable or unstable, all has some pretty real life applications, especially with these types of models.